Let's do one more of these. So this time we're going to solve by graphing negative x squared plus 15x minus 63 equals 0. And this one's already in standard form. It's already in descending order of exponents and set equal to 0, so we're ready to jump right in to find the vertex. So this time a is negative 1 because the number in front of the x squared is negative 1. B will be 15, and C will be 63. So again, using our x equals negative b over 2a formula, that's going to be negative 15 over 2 times 1. Excuse me, 2 times negative 1. Don't forget your pesky negatives, Mr. Quarter. That's going to be negative 15 over negative 2, which is going to be positive 15 halves. So the x value of the vertex will be located at positive 15 halves. And then we plug it back into the original problem. You got to watch out for this because when you plug it in to negative 15 halves squared, notice that I'm not putting parentheses around the negative because the negative is not affected by the exponent of 2. It only affects the x, not the negative portion. So what that means is when we get to the next step, we will only square 15 halves, but we will place a negative out in front of it. So it'll be negative 15 halves squared plus 15 times 15 halves minus 63. And negative and then 15 halves squared winds up to be negative 225 over 4 plus 15 times 15 halves is 225 over 2 minus 63. And probably be quickest to do that with a calculator. And you discover that the answer for the y value of the vertex is negative 27 fourths. So when we graph that, 15 halves is 7.5. So I would go over to 7.5. And negative 27 fourths is about negative 6 3/4. So that's going to place the vertex right here. Oh, let's try that again. That's actually 6.5. Let's move it over one more step. A little off today. How about right there? That's a negative 7.5 and then negative 6 3/4, right there. Okay, then we do the y-intercept, and notice where the y-intercept is. The y-intercept is a c value, which is 63, and that is not going to help us out a whole lot. Trying to highlight that. There we go. Right there. Y value is 63, which is way off the screen right now, so we're not going to bother with graphing the y-intercept. We can still try the 1-3-5 rule. We do have an a value that's negative 1 this time, so we do need to use that a value. Let's use a different color there. There we go. Times the 1-3-5 rule, and that will give us negative 1, negative 3, negative 5. So watch what happens on this one. So from my vertex, I'll go out 1 and down 1, which places the first set of points there. And from there, I'll go out 1 and down 1, 2, 3, which is going to go off the graph a little bit, but we can handle that. But going off down 5 for the next step is going to put us way off the graph. So this is good enough for what our graph looks like. But remember, we're trying to find the solution to the equation, and that's where there are x-intercepts. And this one doesn't have any x-intercepts. So that means that for this one, there are no real solutions. This is the phrase you would use when there are no x-intercepts. There are no real solutions. And I am going to emphasize the word real here because the next couple of sections talks about the imaginary numbers. And yes, there are certain such numbers called imaginary numbers that are important to real-life situations. So don't just say no solutions. Identify that there are no real solutions. Because as you'll see in the next couple of sections, that a question like this does have imaginary solutions. Here's a real-life example, and again, with some of these real-life examples, sometimes it's best that we actually solve these using a graphing calculator. A golfer hits a ball from an elevated tee box 200 feet above the fairway. The height of the ball above the fairway is modeled by h of t equals negative 16t squared plus 28t plus 200, where t is the time in seconds after being hit. How long will it take the ball to reach the fairway? So we're going to go to Desmos. And here we are. So we're going to type in our equation, which was h of t. So I go ahead and I'll just use a y. Y equals, it was negative 16, and we'll use x instead of the t. So x squared plus 28x plus 200. And there's our graph. And what I often get is, well, Mr. Corder, this doesn't look like a parabola to me. It looks like two straight lines. Well, the reason it looks like two straight lines is because we are zoomed so far in that we can't see this really gigantic parabola. So I'm going to have to zoom out a little bit to see the whole parabola, and there I can finally see the vertex of the parabola. It's way up there past 200. So remember the question was, when is the ball going to hit the ground? So the ball is going to hit the ground down here at the x-axis. So when I use Desmos and I click on the x-axis, it's actually going to, there's 2 points down there. There's one at negative 2.7670, and there's another one at 4.5170. So which one of those makes the most sense? Well, since the answer has to be a positive number because we can't have negative time, the answer is actually the positive number. So the answer to this question would be the ball hits the ground at 4.517 seconds. Notice the 0 at that point. 0 represents the height of the ball. So more specifically, we can state that the ball is down at a height of 0 feet at the 4.51 second mark.